So the next talk is by Professor Dibyendu from IIT Bombay, and he is going to talk about stochastic resetting in the presence of potentials. So Dibyendu, you can start sharing.
Can you see my screen?
Yes. Can you make it full screen?
Yeah.
Okay. Yes.
Okay.
So let's start.
Good morning, everybody. The works I am about to discuss were done with my PhD student Sahid Ahmed, and the details may be found in the following publications. So we'll start with a cartoon. A mouse starting at x0 has to reach some target, which is a food source. It may take a short time t, long time t prime. On an average, the time is very large. But this thing can be expedited. This process can be expedited by using a very nice strategy, which was proposed in 2011 by Majumdar and Evans, in which the mouse is put back or reset back to its initial location after a certain times tau, which may be drawn from various distributions. One of them could be an exponential distribution with a certain rate. And if done so, the mean first passage time becomes smaller. So here is a curve. As the resetting rate is raised, the mean first passage time actually lowers, and it reaches a minimum value at some value of the rate, which is R star, which is referred to as the optimal resetting rate, beyond which the mean time again rises. Okay, so this is a nice tunable strategy, and a lot of works have appeared after this work. I mean, it has opened up a huge area, various applications, and even in chemistry, algorithmic studies, and biology, and things like that. But I will just focus on one small issue that we have been interested in, and that is, my God. Okay. So if you have a conventional mechanism, which is that if there is a sort of strong smell, for example, to guide the mouse to its food source, that could also drive it faster to its target. So, for example, mathematically, you would say that there is a potential, and if you raise the strength of the potential, you can make the time lower. So now the question is that what if both these strategies, stochastic resetting as well as the potential drive, are present together? Well, so what happens is that there is a transition. So when the strength of the potential is small, you have the usual optimal resetting rate at a finite value. And as the strength of the potential rises, the R star becomes smaller, and at a critical value of the potential strength, it vanishes. Okay, so that is when you are keeping the reset point fixed. On the other hand, you could sort of keep the potential strength fixed and move the reset point away from the target, and then also the same transition will happen. Turns out that if this optimal resetting rate is now treated as an order parameter, then it vanishes as a power law with some exponent. That is one generically. Why so? I will come to in the next couple of slides. We worked this out exactly for one dimension, linear, quadratic, and box potential, and other works appeared with linear potential, log potential, as well as the box setup in these references. So the next question was that could this be extended to higher dimensions and for any generic spherically symmetric potentials? The general idea would be to solve the backward equation for the survival probability, to get the mean time in the presence of resetting, and to take its derivative and find where is the transition. And this could be done for the logarithmic potential, the box potential, and then linear potential exactly in all dimensions. But if you go to the generic power law potential, that is not closed form answers are hard to get unless there are certain ratios of these parameters d by n and 2 by n, which are integers. Then it becomes a little simpler looking expressions. But for what? The transition point, the full problem cannot be solved, and the transition point can be obtained from this particular identity. So this is interesting. What is this identity? It's an identity of the moments of the first passage time in the absence of resetting. So you see, we are talking of a transition which happens in the presence of resetting as the resetting rate is tuned. But then one is saying that this particular transition where resetting is important to resetting not being important happens with when this particular A1, some constant A1 is 0. Now, what is this constant? It turns out that if you take the mean first passage time as a function of R, near the transition, you can expand it exactly in a series, and then you will have coefficients which will be dependent on the moments of the first passage time in the absence of resetting. That is the origin of these coefficients like A1. A0 is just mean t, A2 has higher moments and all that. And like usual Landau theory, now if you minimize under these conditions, you are going to get this as the transition point. So this is a nice criterion by which you can actually solve the critical point without solving the whole problem. Now, this was elaborated further by Ornopal and Prasad in a very nice paper, and they pointed out something which we had completely missed, which is that within this Landau theory, of course, there is the possibility that A1 and A2 can go to 0. You will have a tricritical point. If A1 is positive, A2 is negative, you will have a discontinuous jump of this optimal resetting rate. And the associated exponents now for the continuous transition will be beta equal to 1, and for the tricritical point half. They give a very concrete sort of example also where this may arise. And that is that you have a one-dimensional diffusive system driven with a constant slope. This potential is a constant slope. And then two absorbing boundaries. That simple problem, if you look at, then as a function of the slope of this potential and this what you may call the driving velocity and the location of the walker where it is being reset, you have this nice phase diagram where one of the lines is a continuous transition line. The other line is a continuous transition line breaking into a discontinuous transition at a tricritical point. So what next? Now you can get a little more complicated by looking at the barrier crossing problem, where the mouse now has to go over a wall to reach the target. And this can be mimicked also in the classic problem that if you are in a valley and you have to reach a hilltop like escape, and then if you reach the hilltop for the first time in that escape problem, what is the first passage time? And in the presence of resetting, where will resetting help to reach the target and where will it not is the question. And numerically, these two papers, Ruveni's group and us, we had looked at, but recently Rishu Singh and Mesler, they looked at these exactly with piecewise linear potentials. But all these papers, what they got actually was that on one side, there is this scenario where resetting helps, but beyond a certain distance, resetting does not help. A very simple scenario. But things become more interesting as we realized, and this is the most recent paper we have. If you actually look at a valley to valley, the full space, and so what one is thinking of, just think of a magnetic system in which the magnetization now can go from negative minimum to positive minimum, while the target is the negative magnetization state. And you are at low temperature. So how low a temperature is depends on the parameter B. B will be large if temperature is closer to 0. And the barrier will be larger. And if you have a magnetic field, then one of the valleys can be made asymmetric with respect to the other. So this is a very classic setting all of you are familiar with. Now we are using resetting to say that where is resetting going to help to actually reach the target and where not. So it turns out that if you are at temperatures which are close to TC, lower but close to TC, that is the valleys are not very deep, then the scenario remains like the old studies, where you are having resetting important on the left side and resetting unimportant on the right side, and there is a phase boundary which is continuous. On the other hand, if you go to low temperatures, where the valleys become deeper, this phase transition boundary actually turns around like this, and that becomes very interesting, because what one is telling is that at such low temperature, between two ranges of field, let's say C minimum and C max, if you are at any field between these two values, then you are going to have patches of magnetization where resetting is important and patches where it is not. So between 0 to U1, resetting will be important. Between U2 to U3, resetting will be important. Resetting will be an hindrance if you are between U1 to U2 and U3 to 1. Okay. And the fact this kind of quartic potential, of course, we had to numerically integrate that equations to get it. There were no exact expressions, but one can actually get exact expressions by mimicking the quartic potential with piecewise linear potentials like this. And there the whole exact calculation can be done. And as you can see that the phase diagram is very similar. So this was a confirmation. Now we move to the more
interesting. Dash, you have 2 more minutes.
Yeah, just one slide. Yeah, so we have this case where both the boundaries are now absorbing boundaries. So let us say the negative magnetization state as well as the positive magnetization state are targets. You leave the magnetization somewhere in between, and then you start the thermal evolution, and once in a while you are resetting it. Now what we are setting here is that the field is a certain value. C is 1.4, let us say. And then we are varying the temperature here and the point of location. So what you see in here is the lines, the transition lines. Right side line is a continuous line. Left side line was continuous above this field, but below this field, sorry. But then suddenly 2 tricritical points appear. And then when you go to higher fields, actually you see that the 2 tricritical points fly apart with a discontinuous transition line in between, and then followed by continuous lines on the 2 sides. This is little exotic because I did not see 2 tricritical points in models before. So this was quite interesting. And this quartic potential, as I said, we can only do through numerical integration, but you can actually do the piecewise linear thing exactly. And that is very instructive because there we can vary V0, this V2 slope as much as we wish from negative to positive values. If you make it negative, which is basically not having a peak, then you return in the bottom half of the phase diagram, which is exactly what Arnab Pal and V.V. Prasad got. Okay, 1 critical point and discontinuous transition. But if you go to the positive, that is when you have a slow, actually a hill, you get these 2 tricritical points, 1 discontinuous transition. And more interestingly, if you actually go to higher values of V, you get a island near the peak where resetting is important. So here for these values, if you are at a particular V2 and you go horizontally, you will actually get 4 continuous transition points. Okay. Those are all shown here. R star, the order parameter, has been plotted as surfaces, and you can see how it comes down, and there are jumps here, and so on and so forth. Okay, so I'm done. So what we learned from these problems is that with potential drive and stochastic resetting, the number of targets do matter. 1 versus 2, because in case of 1, we are always seeing continuous transitions. If it is 2, you are starting to see discontinuous transitions, and also the spatial asymmetry of the potential matters. And potential barrier problems, they are giving rise to multiple tricritical points, and the resetting strategy seems to be important in specific ranges of magnetization, not for whole one side versus another side, which was seen in other simpler models. So thank you.
Thank you, Professor Dash, for this interesting talk. If there are any questions. Yes, there is one question from Shumeda. Yeah, please go ahead.
Hi, Dibyendu, very nice talk. So I have a question about those 2 tricritical points, which are connected by the first order transition. So the ordered phase on the left, which you have in the pink, is it the same throughout?
Same in this sense that here there are not too many sort of stochastic variables one can look at. One is just telling that in this phase, R star is positive. Yeah, in that sense, it is a continuous phase on the, like this pink side all has R star greater than 0, if that is what you mean.
Okay. So recently,
As you can see, this blue and green, everything is R star greater than 0. Only they are jumping to 0 at these transition points and lines.
okay. Recently, we saw something similar in a random field Bloom-Capel model, which
Oh,
we have
wow.
also not seen reported, but there were 2 order parameters. That's the reason I asked. Maybe
Oh, okay, okay. No, here there is, I don't know whether I can call this as an order parameter, because one of the big worry about this is that how do you define fluctuation? So far, we have not seen it very clearly how to do so, because it is this exponent beta we have been talking, but what about other exponents? I mean, but preliminary studies with Ising model, we have started to do. Some of these phase boundaries seem to be there. I mean, it is not altogether, just one body artifact.
Okay, thank you.
Okay, Sriram?
Yeah, actually, Dibyendu, nice talk. My question is related to your last remark just now. You were talking about looking at other exponents, or more generally, I guess, promoting this order parameter to the level of some kind of field theory. So what sort of progress is there in that direction, so that it isn't merely a question of one variable with a potential, but something spatially extended? Is there some way of viewing it that way?
I haven't, I am not informed about any such work having, I haven't seen anything such happening, but we have been thinking, like, it is a little bit difficult. It's like the minimum of the mean time. That is what we are calling as an order parameter. Now,
Right.
What do we mean by the fluctuations? How do we develop it? I mean, these have been open worries for me. Recently we have started doing some simulations with Ising model, where there are many degrees of freedom, and hopefully we will be able to define some fluctuations in some sort of way. But I am not really this thing. But Satya has also worked on some Ising model relation where resetting is done, and he has looked at probability distributions in the steady state and all that, and maybe he can comment if he's there. I don't know.
Yeah, I'm there.
Are you going to comment, Satya?
Yes, I can comment. So indeed, I mean, the field theory has not yet been developed fully, and there have been just, a little bit of work here and there on the, but it's slightly different from what Dibyendu was talking about, because there, the thing was about the first passage time, whereas what has been done, like we have done some work on the Ising model or something. So there, you reset the whole configuration from, you have a, evolving dynamics, and then once in a while, you just go back to the starting point, basically, whole configuration. But there, first passage is not really an important issue. What is the important issue is the non-equilibrium stationary state that it generates, okay? And so there, I mean, for example, I mean, the usual phase transition that you see in the Ising model, when you introduce the resetting, the transition actually disappears in certain cases. So you can ask, how the standard phase diagram changes as you introduce resetting, but not this kind of first passage optimal time that has been studied.
I see.
Dibyendu, can I just ask you one quick question?
Yeah, please.
Yeah, so I mean, you have these two varying things. One is the the resetting rate R, and the other is the potential, right? So what we are studying is optimizing with respect to the resetting rate, but for fixed potential. Did you also try to functionally vary the potential and see what optimal potential would lead to the minimum first passage time?
So in a sense, we are varying the potential, but we haven't done it systematically. That's my answer.
Yeah,
I mean,
we are looking at only piecewise potential.
Yeah. So we are varying the different slopes continuously, and we are seeing that there is an optimal point. In that sense, we can say there is a scan.
No, but I'm asking that, I'm asking that you may not have a piecewise continuous potential. It may not be the best thing, right?
Achha.
It could be something else. I mean, you can functionally vary. If you calculate the mean first passage time as a function of the resetting parameter R and as a functional of the potential under which it's moving, and then when you vary functionally and find out the functional minimum, which potential actually leads to the best mean first passage time. So
okay, but that will be with respect to some parameter form of the potential where the parameters will be varied.
You can do a functional integration and find out what is the potential. This has been done without resetting. This has been done. There's a huge literature on that.
Okay.
And you
Okay,
can
maybe
ask
I'll write
what
to you.
happens in
Yeah.
presence of resetting.
Sounds interesting. I mean, please do. I will write to you. Yeah.
Sure. Okay. Okay.
Okay, there is one last comment from PK in the context of having more than one tricritical point. So he's saying that there are fiber bundle models with continuous line of tricritical points, and he has also given a reference if you want to check it out.
Okay. Okay. In the chat box.
In the chat box, yes.
Yeah,
PK,
thank
if you
you.
have something else to say, you can unmute. Or maybe he's having trouble with the mic. But this is a reference of a PRL from 1997.
Yes, I will just, yeah, thank you. Yeah.
Okay. Okay, so if there are no other questions, let's thank Professor Dibyendu once again.